You type a question, hit enter, and watch as an eloquent, perfectly formatted essay streams across the screen in seconds. It feels like there's a highly educated, articulate entity sitting on the other side of the keyboard. There is nothing inside these racks that understands a single word you wrote. There's no empathy, no comprehension, and no ghost in the machine. This technology is built on decades of academic research and massive data processing at institutions like Stanford. At their core, large language models, or LLMs, are essentially hyper-advanced versions of the autocomplete feature on your phone. The ability to generate code or poetry comes from a specific neural network architecture known as the transformer. To see what's actually happening, we have to strip away the friendly chat interface and follow exactly what a single text prompt goes through once it enters that black box. The journey starts with a basic limitation. Computers cannot read English. They don't recognize letters or words, they only process numbers. So before the machine does anything else, your prompt is sliced into pieces through a process called tokenization. A sentence is broken down into smaller fragments, sometimes whole words, sometimes just individual syllables, called tokens. Each one of those fragmented syllables and words is then assigned a specific number from a massive dictionary database. This rigorous translation from human prose into raw mathematics is the required first step. It is the only way a machine can begin to interact with your request. Once your words are converted into numbers, those digits enter the core processing layer, the transformer model. Older language systems read sequences strictly from left to right, one word at a time, which meant they often lost the original context by the time they reached the end of a long sentence. The breakthrough of the transformer is something called the attention mechanism. Instead of reading linearly, it allows the model to look at every single token in your prompt simultaneously. It calculates mathematical weights between every word to determine how they relate to each other. This is how the system grasps context, differentiating the bank of a river from a financial bank based entirely on the surrounding tokens. This immense, multi-dimensional map of calculated relationships isolates the specific intent of your prompt. It's an intricate mathematical structure that creates a highly convincing illusion of reading comprehension. Now that the model has successfully mapped the context of your question, it has to write an answer. Looking at this dynamic bar chart, we can see exactly how it generates that response. The model isn't forming an entire idea at once. It is simply calculating the statistical probability of what the single next token should be, selects the winner, and locks it into place. It takes that new word, recalculates the entire context, and predicts the next one. It repeats this single predictive step thousands of times a second to build out sentences, paragraphs, and entire essays. Left to its own devices, this raw predictive power can generate erratic text. That's why human engineers perform a crucial step called tuning, or post-training. They adjust the model's guardrails to ensure its probabilities output useful, structured responses. Every essay, joke, or line of code you've ever seen an LLM generate is the result of a rapid-fire, highly supervised sequence of mathematical guesses. When you return to that clean chat interface and look at the response, knowing how the engine works changes how you evaluate what you're reading. It explains why AI suffers from hallucinations, those moments when the model confidently invents historical events, citations, or data out of thin air. The system is doing exactly what it was built to do: generate the most statistically plausible sequence of words. It does not reference an internal database of absolute truth. It calculates the highest probability. And sometimes a false statement is highly probable. Because these models are explicitly engineered to sound articulate and convincing, treating them as infallible oracles is a dangerous trap. They are persuasive, but they are not inherently truthful. Engineers are already moving past simple text prediction to solve these limitations. The focus has shifted toward building what are known as agentic LLMs, or compound systems. Instead of relying entirely on predictive guesses, the base model is wrapped in external tools. It independently browses the web, runs calculators, or executes code. This structure allows the system to pause, verify its work, and correct its course before answering, becoming an active problem solver. Stripping away the illusion of sentience reveals the machine's true utility. It is an assembly of mathematical probability and external verification tools, a system designed for precise execution rather than conversation.